We are going to start with the topic of GPS, the invisible grid, the mechanics of GPS. First, we need to know the full form of GPS, right? GPS stands for Global Positioning System. As you can see in the image within the slide, it's about the position of. We are going to go for the topic of GPS, the mechanics of GPS. First of all, you need to know what GPS stands for. GPS stands for Global Positioning System. Here you can read the text which says how atomic clocks 20,200 kilometers in space pinpoint your exact location on it. You are going to get to know what it actually means in the coming slides. So let's go for the next slide. Okay. The first of all, there's an illusion in regards to GPS. Okay. GPS actually does not track you. It's about the GPS is completely based on the working of the satellites, and the satellites only broadcast signals to our device, and our device only listens. So there is nothing sort of tracking when it comes to GPS. What actually tracks us is the software which is installed within the phone for the global positioning system. Okay. So you'll get to know what actually happens is that it's completely based on four metrics: latitude, longitude, altitude, and time. These are the main metrics on which the global positioning system works on, and also the speed you'll get to know. So, what is latitude? Latitude is the distance from the equator, like those are the horizontal lines. And longitudes are the vertical lines. So I might have said that simply, but what actually it is that latitude is about how north or south you are from the equator. Like that distance, that particular metric is called as latitude. So you need to think of it as horizontal lines across the earth. Longitudes measure how far east or west we are from the prime meridian. Altitude is the height above the sea level, and you know what time is. So the time which is mentioned in here, the metric, is not the normal time which we use. There is a lot of difference between the clock time which we are using and the actual time which is calculated for, which is very more precise. Those are called as atomic clocks. Atomic clocks. So what actually happens is that time is calculated based on atoms, the vibrations of atoms. Okay, cesium is the most common one which is used for the atomic clocks, which is the first practical atomic clock which has been released during the 1900s. Okay, these four are the main metrics along with speed. The space segment, atomic accuracy in the orbit. Okay, there are 30 plus active satellites in the atmosphere. which are for the global positioning system. And the altitude here means that the distance from the surface in which the satellites revolve is 20,200 kilometers. And I have mentioned previously about the atomic clock, right? Yeah. So the how the satellite works is based on completely based on atomic clocks. Like the hardware which is used is the atomic clock. The payload, exact current position, it's based on the Cartesian coordinates x, y, z, which are latitude, longitude, and altitude. Exact time the signal was transmitted. So it's about when the satellite sends the signal that is considered as the time in which the signal has been sent. The core mechanism. So how we are actually going to calculate the distance between the satellite to our device is that it's based on when we receive the signal to the when it has been sent. That is considered as delay, and we are going to multiply it with the speed of light. Then we will get the distance between the satellite, which has sent us the signals, and to our device. The speed of light is around 300,000 kilometers per second. Okay, so for suppose if there is a delay of 0.07 seconds, we are going to multiply it with 3 lakh kilometers per second, and we are going to get around 21,000 kilometers distance between our device and the satellite which sends the signal. The phone simply calculates this delay to determine how far away the satellite is. Okay. Trilateration is a technique which is utilized for the GPS. So, what actually is trilateration is that it is completely based on uh, the latitude, longitude, altitude, and the exact time in which the signal was sent. So, how it actually works is that, for suppose there is a satellite which is sending the signals, it is going to calculate the position, the latitude, longitude, altitude, and the exact time the signal is sent. And our phone receives the signal. So, this is the payload which the signal carries. And our phone is going to calculate it based on the time in which it has been delivered to us, minusing the time it has in which it has been sent with the speed of light. Based on that, it is going to calculate the distance. So what the slide is saying is that one satellite is going to show what somewhere on the sphere's surface. Two satellites is going to have the intersection, a circle of possibilities. Three satellites intersect intersection, two exact points in space. But these satellites are not enough. For the trilateration, for this method, we require four satellites because we have a total of four different metrics. So that's the reason we require four satellites to precisely calculate the GPS for the latitude, longitude, altitude, other time. The 4D equation. Why four satellites? We'll get to know here. As I mentioned previously, so the reason why we require the four satellites is for the four variables because they are the four variables which we need to calculate, right? This is very important because even nanosecond errors can cause massive distance miscalculations. As you have seen it before, there's a lot of distance between the satellite and where the satellites are to the surface, right? That's the reason. Full system architecture. So you can see that within the space segment, like the satellites are going to calculate the Cartesian coordinates, or the X, Y, Z, and we have the control segment, which is going to track the satellite's health to make sure the satellites are working properly and the orbital paths. and the user segment, which is going to receive the signals, and it is going to convert the 3D space to latitude, longitude, and latitude. And this is going to be a continuous operation, which is going to be recalculated each and every second. That's how whenever you walk for each and every second, the GPS changes. The obstacle course. There are a lot of different ways in which errors can occur in GPUs. It is based on the different sphere areas in the layers of the Earth, troposphere, which is the surface area, where we can get signal bounds of from for because of buildings before reaching the receiver. That's considered as the multipath error. And we have the ionosphere and the midsphere, where these spheres physically slow the radio signal. This is considered as atmospheric delay. And we have the upper atmosphere, where there can be clock errors, tiny timing discrepancies equate to massive distance errors. And we have the satellite position errors, slight orbital deviations from predicted paths. So these satellites orbit around the Earth, right? So if there are any errors, any deviations in that, it will cause deviations from the predicted paths. So these are the four main different types of errors which can occur when GPS is calculated. Satellite position errors, clock errors, atmospheric delay, multipath error. Error correction diagnostic matrix. DGPS, these are the different types of GPS systems. Uh, Here we can see three different types of systems. DGPS, which is a differential GPS, AGPS, which is the assisted GPS, WASS, which is the wide area augmentation. So let's see what mechanism they follow. DGPS uses fixed ground stations to calculate local error. So the ground stations are going to be stationary stations where the local error will be calculated. So that's the main mechanism behind differential GPS. Assisted GPS downloads satellite orbital data via cellular internet. So it is going to use the data from the satellite orbital data. And we have the wide area augmentation. So this is a network of ground stations broadcasting via dedicated satellites. So there are going to be dedicated satellites for this. And we can see the main use cases for these different types of systems. For DGPS, it is mainly used for professional surveying, maritime. AGPS, smartphones. WAS, aviation. We can see the accuracy gain based on the different types of systems too. The accuracy is high for DGPS, drastically faster lock time for AGPS, extreme precision for aircraft when it comes to WAS. Multi-constellation architectures. Modern receivers do not rely on a single system. They simultaneously tap into GPS, GLONASS, Galileo, Beidou. These are the different types of systems which are for the global positioning system, like various different types. So, which are by different types of by different countries. GPS is developed by USA, where the defense system of USA has developed the GPS. GLONASS by Russia, Galileo by EU, European Union, Beidou by China. More visible satellites at any given moment equals a faster lock and higher accuracy. Okay, standard accuracy is 5 to 10 meters. Advanced combined systems achieve less than 1 meter. That's considerably very high precision. Deriving dynamics, speed and direction. GPS does not directly measure velocity like a physical speedometer. Speed. calculated dynamically by measuring the exact change in position over a specific interval of time. So let's consider from position A to position B. Direction derived mathematically as a vector drawn between sequential coordinate positions. Like for suppose, as you can see in this Cartesian line, where there is the x coordinate and the y coordinate, the position between A to the B, position B, and the direction will be from the position A to the position B. Calculate it continuously in the background. This is always calculate when it comes to the GPS. Vulnerabilities and limitations. Signal weakness, jamming, spoofing. These are the main vulnerabilities when we have GPS. Signal weaknesses, as we have talked before, because of the Earth's atmosphere, there can be delays. We need to have a clear sky view. Signals are severely degraded or entirely blocked indoors, underground, or underwater because the signals and the objects can cause disruptions. Okay, so that's the reason we require a clear sky view. That's the reason when we have rains coming, the signal will be weakened. So not only for GPS, like for suppose we have the dish uh, for dishes, it's based on signals, right? So the reason why those dishes will work is because of the signal disruptions when we have rains or when it's very cloudy. Jamming because space signals are extremely faint upon reaching Earth. They are easily drowned out by localized terrestrial radio noise. Suppose there are a lot of devices running within that particular place, then the signals can be jammed because the distance which these signals travel from the satellites to the surface is in thousands of kilometers. We have read about it before, right? 20,200 kilometers. Spoofing. Civilian bands broadcast as unencrypted one-way signals. Fake transmitters can trick receivers into calculating completely false locations. So these type of things can happen due to cyber attacks. Spoofing is a type of cyber attack. The privacy misconception. Who is tracking you? So, as we have talked in before, the GPS is not the network which is going to track us. It's just a one-way signal. Okay, it is not going to track us. It doesn't receive any information. That's what I mean when it comes to one-way. It can only send signals. It cannot receive signals from our devices. Okay, so it's mathematically impossible for a GPS to track a user because it doesn't receive any signals. It only sends signals. The tracking actually happens in the app layer. The software is the one which tracks us, not the satellites. When people say GPS is tracking me, they are referring to the mapping apps. For suppose if you are using Google Maps, the tracking software is within the Google Maps. It's not within the GPS. Okay. They are referring to the mapping apps, taking the offline map solved by the phone and transmitting it over the internet. Okay. So it is going to be transmitted over the internet. And it's by the software and not by the GPS, not by the satellites. So we'll go for the end-to-end system pipeline. First is the broadcast, second is the transit, third is the reception, fourth is the trilateration, fifth is the output. Broadcast. Space segment transmits time plus orbital position. Orbital position is the x, y, and z coordinates, which are the latitude, longitude, and attitude. Transit. Signal navigates atmospheric delay and multipath interference. So the signals are going to be transmitted from the satellites towards our devices. Reception. Our device is going to receive the transmitted signals from the satellites and it is going to note down the arrival time and calculates the delay. This delay needs to be calculated to calculate the distance which will be calculated based on the delay into the speed of the light, which is 3 lakh kilometers per second. And the delay is calculated based on when the signals are received minus the difference between the signals received to the when the signals have been sent, and it is multiplied by the speed of the light to get the distance. The triliterations. This is a method which is used by the GPS. It receives data from the 4 plus satellites. So we require minimum 4 satellites, as we have talked before, because there are 4 variables: latitude, longitude, altitude, and time. So it solves the 4D equation, and yeah, output. 3D coordinates convert it to latitude longitude mapping, revealing the blue dot on the screen. So that's how we are going to get the uh, we are going to get the tracking of the where we are actually located within the map. So these data which we are going to receive, these 3D coordinates are going to be converted into latitude longitude mapping within the map.